Good afternoon, everyone. Welcome to this Wook Hyun Kwon Lecture 2025. Let me just briefly introduce about this Wook Hyun Kwon Lecture series. I'm the professor, my name is Hyungbo Shim, and I'm the professor of the Department of Electrical and Computer Engineering, and I'm the organizer of this event. So before talking about this series, let me briefly introduce about Professor Wook Hyun Kwon. And he received a bachelor degree and a master degree at Seoul National University. And he got a PhD degree at Brown University in 1975. And he became a professor at Seoul National University more than 30 years. And then after his retirement, he became a chair professor at the Daegu Gyeongbuk Institute of Science and Technology for more than 4 years. He is dedicated to the field of predictive and receding horizon control and time-delayed system, FI filtering, and real-time computer and application for automation. And he supervised more than 100 graduate students, including 55 PhD students. And he published 150 international journal papers and 260 conference papers. He actually wrote 2 textbooks. One is for the receding horizon control, the other one is time delay control, which has been published in Springer 2 times. And he is a fellow of National Academy of Engineering of Korea, fellow of Korean Academy of Science and Technology, fellow of IEEE and the International Federation of Automatic Control, and the World Academy of Science. And he is former president of IFAC, ICROS, which is Institute of Control and Robotics and System, and Korean Institute of Electrical Engineers. And he was the former vice president of this National Academy and the Korean Academy of Science and Technology. He was a motivator of entrepreneurship. So he fostered 10 startups by his students, and 7 out of which actually went to KOSDAQ, which is a Korean version of NASDAQ. He was elected as Korean Meritorious Scientist and Engineers in 2019, and he became a member of US National Academy of Engineering 2022. So, in order to honor Professor Kwon's lifetime influence and contribution to the community, this series of lectures was initiated in 2016. And every year, a person who made a great contribution to the system and control area is invited and asked to deliver a lecture. And this lecture is then recorded and broadcast online to the public in order to disseminate the knowledge and wisdom of the invited speaker. So far we had Thomas Kailas, Alberto Istori, Stefan Boyd, and Manfredi Morari, Brian Anderson, Tamer Bassar. And finally, this year, we are very happy to have Professor Steve Morse this year. This event is made possible through the donation by Professor Kwon and his former students, and I would like to take this opportunity to thank all of them for their endowment. And also I thank the support of Korean NMO, National Member Organization of IFAC, which is ICROS. I hope and believe that this lecture series continues delivery of the knowledge and the wisdom of the invited speaker to the young researchers of next generation, so that they will also contribute to the community and the world in the future. This event is organized and managed by the Engineering Research Center for Advanced Control and Instrumentation. It was founded by Professor Kwon in 1991 as the ERC program supported by Korea Science and Engineering Foundation, and it is one of the most successful ERC. And it is now working for education and propagation of knowledge. Also, we are proud member of the Department of Electrical Computer Engineering at Seoul National University. So, now I would like to invite our chair of the department, who is Professor Yong-taek Kong. The podium is yours. Please give a big applause.
Thank you, Professor Jim. Let me read through the paper that I prepared here. Good afternoon, participants and the guests, and the Professor Wook Hyun Kwon and Professor Steve Morse. It is a great honor for me to be here today. On behalf of the Department of Electrical and Computer Engineering at Seoul National University, I would like to extend a warm welcome to all of you and offer my sincere congratulations on the occasion of this year's Kwon Lecture Series. This year has been particularly meaningful for me, as I have had more opportunities than ever before to meet Professor Kwon in person. Just last month, our department celebrated the 30th anniversary of the unification of three formerly separate departments: electrical engineering, electronics engineering, and control and measurement engineering. Professor Kwon had the foresight to recognize the importance of unification in strengthening our global competitiveness, and he played a leading role in bridging the departments together. Thank you. Thanks to the vision and leadership of Professor Kwon and our senior faculty members, our department has grown significantly and has made remarkable contributions to both academia and industry. Our alumni had gone on to lead innovation across diverse sectors, helping to position Korea as one of the most technologically advanced and innovative nations in the world. In this light, it is especially meaningful to welcome Professor Steve Morse today. I got help from ChatGPT to check Professor Steve Morse's achievement. I know the Professor Kwon will introduce him in detail. Professor Morse, this is the ChatGPT description for you. Professor Morse is one of the most influential scholars in the field of control systems and systems theory. His pioneering work on control and estimation, hybrid systems, and networked control has laid the theoretical foundations for many modern technologies. His research has shaped the way engineers design, analyze complex large-scale systems, including autonomous systems, robotics, and multi-agent networks. As a member of the U.S. National Academy of Engineering and a recipient of numerous prestigious awards, Professor Morse's contribution has had a profound and lasting impact on global electrical engineering and system science. I would like to express my deepest gratitude to Professor Steve Morse for joining us today, and to Professor Wook Hyun Kwon for his continuing inspiration and leadership. I also sincerely appreciate the dedication of Professor Hyung-bo Shim and the Engineering Research Center for Advanced Control and Instrumentation for initiating and organizing this outstanding lecture series. I hope today's lecture will be both intellectually stimulating and inspiring for all participants who are here today. Thank you very much. And let me introduce Professor Wook Hyun Kwon. Why don't you give him a big hand so that he can introduce the lecture.
Good afternoon. It is my great honor to introduce this distinguished scholar from Yale University. Please excuse me for the hoarse voice. I got a slight cold. He was born in Mount Vernon, New York. I checked the map. So it's close to New York, but a little different. He started from this area. He had a Bachelor of Science from Cornell University in 1962 and Master of Science in Engineering from University of Arizona in 1964 and PhD from Purdue University in 1967. Then he was the Office of Control Theory and Application of NASA Research Center from 1967 to 1970. Since 1970, he has been a professor of Yale University. He's still working, he's not retired yet. His research area, system theory, network synthesis, optimal control, multivariable control, adaptive control, urban transportation, and vision-based control, hybrid and nonlinear systems, and sensor network, and coordination and control of large grouping of a mobile autonomous agent, maybe today's topics. Professor Hong and the chairman of my department explained him very well. Thank you. I saw his Google Scholar citation is enormous. Whole total citation around 50,000. And if you see the over 1,000, 1, 2, 3, 4, 5, 6 paper cited over thousands. Usually, book obtained high citation, but in his case, different. All papers got very high citation. That means he's a really distinguished scholar in his area. So I look at his award and honor. His RTP System Award in 1997. This is the highest award of RTP Control System Society. He received the Koza Medal, IPAC, in 2023. This is the highest award in IPAC. And Rich Bellman Control Hedge Award from AACC. This is the highest award of AACC. He received the highest award all different sectors. No other highest award in this area. And he also received the Georgia XLB's Outstanding Paper Award and Automatic Theory Methodology Prize and the American Automatic Control Council's Best Paper Award. He received a lot of best paper, but based on this, he could receive the highest award. He became the fellow of IEEE in early days, and he is also fellow of IFAC in 2014, and he became member of U.S. National Academy of Engineering in 2002. It's been early age. To be a member of U.S. National Academy in USA is one of the highest professional distinction accorded to the engineer in the United States. Thank you for your attention. Let's let's invite Professor Steve Morris.
Today, as they say in Australia, it's a very nice introduction. I thank you, all of you, and this is my first time in Korea. And as I landed at Incheon Airport after a delay because of the volcanoes erupting over Russia and a necessity to change the route of the airline, we landed in Tokyo, and then after a few hours, we finally reached Incheon. And as we landed, I couldn't help but remember the first time I heard the word Incheon. I was quite young, and it was when the U.S. troops were landing in Incheon during the Korean War. And so and there I was landing in Incheon, which I found interesting. So I prefer to use this. Okay. Okay, thank you. Okay, so I don't, I want to give a few thank yous. First of all, as you know, this is a lecture named for Professor Kwon, and we go way back together. He was a graduate student at Brown University, and we both attended very nice workshops that were organized for graduate students to give presentations, and this went back to 1972. So we go way back, and I certainly thank you for the very nice introduction. I also thank Professor Shim for his very creative organization of this lecture. It takes a lot of work to put up with people like me. It takes a tremendous amount of work to get everything to run smoothly, and he's done a wonderful job. So with that said, I think I will pivot to my talk directly. Let me change my glasses so I can see see a little bit better. So the title of the talk is Distributed Averaging, Consensus Distributed Averaging and Their Applications. And I want to start, since there's a mathematician in the room, and I know a lot of you think mathematically, I want to start with a theorem. It's well known, it's called the largest integer theorem. And please watch this very carefully, because the proof is very important. So the theorem states, as you all know, that 1 is the largest integer. And I'm going to give a proof by contradiction. So let's let n be the largest integer, right? To prove that n equals 1, suppose the contrary, in which case n is greater than 1. Note that n plus 1 is greater than n. Moreover, n plus 1 is an integer, right? But this is a contradiction because by hypothesis, n is the largest integer. Therefore, by contradiction, the theorem is true. QE did. Okay, I see you're awake. I was going to say that's a joke, you're supposed to laugh, but you're way ahead of me. Okay, so the first thing I'm going to talk about is consensus. These are wildebeest. That's an animal stampeding in the Serengeti in Tanzania in Africa. What in the world does that have to do with consensus? Well, more than you might think. First of all, I should remind you it's the Lion King and also give you a choice. At this point, I can either stop the lecture and we can watch the rest of the Lion King. No? Okay. Okay. So there is a fellow named Craig Reynolds. He's a computer scientist. And in 1987, he came up with an idea called Boids. Now, Boids, if you know Brooklyn, New York, is the way somebody might say birds, but they say Boids. And I always try to make this joke. Of course, it means less to you because your native language is not English, so it's a little tough to understand. But I was curious enough to contact him a few weeks ago and ask him how he came up with the word Boids, and it has nothing to do with Brooklyn, New York. I was going to include the description, but it was too long, so we'll skip it. Anyway, what is a Boid? That's a Boid. Boid is a little green triangle, And imagine in your mind that there is a whole bunch of green triangles, a flock of green triangles moving in the plane. And what Reynolds did was come up with some rules to make sure that these boids all do what they're supposed to do. The gray region is called the sensing region, and at any particular instant of time, any of the boids in that region is a neighbor of this particular boid. Okay? So he came up with 3 rules. They were called flocking rules. The first one is a separation rule. These were not written with mathematical equations. They were written, he's a computer scientist, it was just programming language. First one is a separation rule to make sure that the boids don't hit each other. Second one is an alignment rule to make sure they eventually move in the same direction. And the third one is a cohesion rule, which makes sure that they don't go apart. It's important to keep in mind that the rules are local. The rules are only involved for each boid only involves its neighbors. So they're local rules. So this is a video generated by a fellow named Dmitry Tarazopoulos, and he is using the Craig Reynolds flocking rules. But so was Disney in The Lion King, and because of that, Craig Reynolds won an Academy Award. We're going to deal just with the alignment rule in this lecture. In truth, I first learned about this subject not from The Lion King or Craig Reynolds, but from somebody completely different. I had a student who had been Chinese guy who had been trained in physics and was at Yale looking for a PhD problem, and it was natural for him to be looking in Physical Review Letters, which is a top journal in physics, and he ran across this paper by a bunch of Hungarian guys. Tamás Vasak was the lead author, and they were concerned with the phase transition of self-driven particles, which mathematically was very much like the Craig Reynolds problem. One thing I want to emphasize is that you notice in the first line of the abstract, it uses the word emergence of self-ordered motion. And I'm going to say more about what these words mean, but I want to pivot away from this subject a little bit and talk about an emergent behavior. Now, you watch very carefully because you may want to answer some questions. So consider yourselves, everybody in this room, as comprising a network of M individuals in this lecture hall. Okay? Take your friends to be those in the hall who you really like. You are then a neighbor by definition of each of your friends. Okay? Of course, there may be individuals here who like other individuals in the hall, but the feeling is not reciprocal, so neighbor relations may not be symmetric. Let's let N denote the directed graph on M vertices with a vertex I representing individual I. And let Ij be an arc in the graph just in case individual I is a neighbor of individual J. Suppose the directed graph characterizing neighbor relations is strongly connected. That means that you can get from one vertex, any vertex to any other vertex. Suppose in addition that you have a real number which you text on your nice cell phone to your friends. And suppose that everybody in the room does this. Suppose that right now your number happens to equal the average of the numbers all your neighbors have sent to you. Suppose that this is true of everybody in the room. So I've described a local configuration. You're only dealing with your friends. But there is an emergent behavior. Everybody in the room has the same number. Why is that true? Well, because of time, I'll give you an answer. There are two ways to address this problem. One is to use something called the Perron-Frobenius theorem, which I will mention, at least a form of it, later in the talk. But right now, let's do a direct answer, which is not so fancy. So here's an answer. Let's let script n sub k denote the labels of individual k's m sub k neighbors. M sub k is greater than 0 because each agent is a neighbor of itself. Each person is a neighbor of itself. By assumption, each individual's number is the average of its neighbors, so that's the formula. Call an individual a superagent if its number happens to be as large as any other number of anybody in the room. And a superagent, like any other agent, satisfies the same averaging rule. And if I take this equation, I can write this one. And if you look at this, and keep in mind that we're talking about agent I being a superagent, that means that xi is greater than or equal to all the xj's. That means each of the terms under the summation sign is non-negative. On this planet, you can't add up a bunch of non-negative numbers and get 0 unless all the numbers are 0. So therefore, all of the neighbors of individual I have the same number as individual I, and therefore they're all superagents. So we've already proved that all neighbors of any superagents are themselves superagents. Call a distinct neighbor of individual I, an agent J, a distinct neighbor of agent I if there's a directed path in the graph from J to I. By induction, and I'm not talking about what Michael Faraday invented. That's a joke, you're supposed to laugh. By induction, all distinct neighbors of any superagent are themselves superagents. For a strongly connected graph, every individual is a distinct neighbor of every other individual. Therefore, if n is strongly connected, everybody must be a superagent. Therefore, if n is strongly connected, all xi must be equal. QED. You got it? Okay. I usually ask this question on PhD defenses. No, I don't. Conclusion, to reach a consensus on a strongly connected graph, all we have to do is make sure that everyone's number equals the average of his or her neighbor's numbers. Back to Visick. So what Visick did was to simulate a flock of n agents or particles all moving in the plane with the same speed s, but with different headings, heading being the direction in which you move, theta 1 through theta n. Each agent's heading is updated at the same time as the rest using local rule based on the average of its own current heading plus the heading of its neighbors. Visick simulations demonstrated that these nearest neighbor rules can cause all agents to eventually move in the same direction despite the absence of a leader and or centralized coordination, and despite the fact that each agent's set of neighbors change with time because everybody's moving around. So here's a couple of simulations using the Visick model. This is a standard, these were done by my ex-student, the guy who came up with this line of research, G. Lin. Here's another example which shows that if you just use the heading rule that you might get a bifurcation unless you don't take precautions to make sure that people stay together. So let's look more deeply into the problem. I've got a bunch of agents. And from now on, I'll use the word agent. So this is agent I with label them. Each agent has a sensing region. They don't have to be circular, but that's for this talk, let's just assume that they are. Radius Ri. The neighbors of agent I at any particular instant of time are any other agents which are in its sensing region. Each agent is a neighbor of itself because it's at the middle of its own sensing region. Each agent has its own sensing radius. So neighbor relations are not symmetric. So we're revisiting some of the things we already saw before. The update equation looks exactly like this. It's an averaging rule. Script n sub I of t is the set of labels of h and i's neighbors at time t. And n sub I is the number of labels in the set. Since each agent is a neighbor of itself, n sub I is always positive, so I can invert it without any problems. This becomes the average. Now, I will say that there is another rule which looks something like this. The mu ij are non-negative numbers which sum to 1 and for technical reasons are bounded below by constants over here. And this is really then a convex combination, and I refer to these as convex combination rules. And almost everything I'm going to say applies to this kind of rule, just like it does to the straight averaging rule up here. So the flocking problem then becomes, under what conditions do all n headings converge to a common value? Okay, to dig more deeply into this, we need to define some stuff. So we have a bunch of neighbor sets, given a bunch of neighbor sets, subsets of say the integers 1 through n, 1 through m or whatever, n, 1 through n. Then we can, and let's let script G denote the set of all directed graph with vertices 1 through n. I'm now going to define a graph in G, which has an arc from j to I whenever j is a neighbor of agent I. Very straightforward. That defines a graph. That's an example of such a graph. And you see there are self-arcs at all vertices because each agent is a neighbor of itself. I will use the term neighbor graph, but self-arc will also come up, and it is quite important that the graph be self-arced. Okay, now what I want to do is since I want to analyze what's going on, I want to build from this a state space model. To do that, I have to introduce a matrix or two. First one is the adjacency matrix of a graph. So this graph has an adjacency matrix. An adjacency matrix is simply an n by n matrix with zeros and ones, with the ijth element being a 1 whenever there's an arc in the graph from I to j. So it's very straightforward. And that is the adjacency matrix of this particular graph. And you notice there is the arc from 1 to 2. And so if you look at the 1, 2 element, sure enough, there is a 1. And that's the way you define the adjacency matrix. Next thing is the integree of a vertex, which is simply the number of arcs entering the vertex. So for vertex 2, for example, the integree is 4. There are 4 arcs entering vertex 2. The out degree is the opposite. It's the number of arcs leaving, and the out degree is 1. Now, it's no accident that if I add up the bunch of 1s in any column of this matrix, I get the out degree corresponding to that column. And that will be important in terms of what I have to say next. What I'm going to define now is something called a flocking matrix, F sub n. It's a matrix determined by a neighbor graph. And it's given precisely by this formula, the inverse of a diagonal matrix, non-singular diagonal matrix, whose entries are the integrees of the vertices on the graph, or alternatively the number and D2 is the number of neighbors of Asian 2. So all the numbers in this diagonal matrix are positive. So I can invert it without getting a headache. And the other matrix is the transpose. Prime denotes transpose. It's the transpose of the adjacency matrix. Then I multiply them together, and that defines the matrix which I call a flocking matrix. The graph uniquely determined the flocking matrix, and later I will show you that given a flocking matrix, it will uniquely determine a graph. And when that's the case, mathematicians like to say there's a bijective relationship. These two data sets are equivalent. There's the same data in both sets. Again, these are the update equations, Visick update equations. And so next step is to take the heading variables and arrange them in a column vector. And once you do that, it should come as not a great surprise. Then you end up with a state space model which looks exactly like this on the bottom of the slide. So the Visick problem can now be stated as under what conditions do all n headings eventually converge to a common value. And you say, heck, that's linear recursion equation. It can't be that bad. But it is pretty bad. And the reason it's bad is because the matrix is a function of time. If it wasn't a function of time, you could use eigenvalues and eigenvectors, and one way or another you could figure out what's going on. But in this case, it's more complicated. There is, for example, no common quadratic Lyapunov function, which works for all t. So we have to dig deeper in order to analyze this particular system. So what people do is say, okay, let's iterate the equation a number of times and rewrite the current state at time t as a product of flocking matrices going back to the initial state. That's pretty straightforward. It then becomes clear that the problem that we're trying to solve reduces to finding conditions on the sequence of neighbor graphs that are generated so that the limit of the product of the flocking matrices is a rank 1 matrix of the form 1 times a row vector C. Because if this is true, then the limit of the theta vector has got to be this matrix times the initial value of theta, and that, doing a little algebra, says that the limit is equal to this scalar times 1, which means that all n headings converge to the same value, and we've reached a consensus. So this is what we want to do. We want to find out when this limit exists and is equal to this. Okay, to dig more deeply into this, we need the notion of a row stochastic matrix, or often just called a stochastic matrix. This is a very easy idea. So a square matrix is stochastic if 1, it has only non-negative entries, and 2, if you add up the numbers in any row, you get 1 every row. Now the second condition is entirely equivalent to the matrix having an eigenvector consisting of 1s and an corresponding eigenvalue of 1. So this statement is equivalent to this. Now just let's notice something. If I have two matrices which only have square matrices which only have non-negative entries, and I take their product also only has non-negative entries, because all you do when you do matrix multiplication is addition and multiplication. There are no minus signs generated, so everything stays non-negative. Secondly, if I have two matrices which satisfy this condition, then so does the product by this little argument. So these are the properties of a stochastic matrix, and we reach the conclusion that if we have two stochastic matrices and take their product, we end up with a stochastic matrix, or stochastic matrices are closed under multiplication. Now what about a flocking matrix? Where does that fit into this? So there's the graph of a flocking matrix. And as I put down before, here is the adjacency matrix. And if I add up the numbers and add up the numbers in every row, I end up with these numbers. If I transpose the adjacency matrix, that's what I get. If I take these numbers and make them the diagonal entries on a matrix, and then invert the matrix, this is what I get. And then if I take the product, this is what I get. And if you look at this matrix, it has only non-negative entries, and the sums of the numbers in each row is 1. So it's a stochastic matrix. This is true for every flocking matrix. So flocking matrices are stochastic. But flocking matrices are not closed under multiplication. It's all right, it's true of stochastic matrices, but if I take the product of two flocking matrices, the product is no longer flocking matrix. This says that if I'm going to proceed further and I don't want to get into trouble, I'll be better off looking at products of stochastic matrices rather than products of flocking matrices. If I can make some statements about stochastic matrices, rather than they will apply to flocking matrices, and since I have the closure product with stochastic matrices, the math is going to be easier. So that becomes the problem. So we've gone through a number of steps to try to reduce the problem down to a fairly succinct, easily explained algebra problem. The same problem, one gets the same problem if one uses convex combination rule that I mentioned before rather than the averaging rule. Now, this particular problem is a well-studied problem in what's called the theory of non-homogeneous Markov chains. Now, this comes out of probability theory, Markov theory, and stuff like that. But this material today has nothing to do with probability theory. Algebraically, there's an overlap, but in terms of probabilities, 0 overlap. Okay, let me right away state a result, which is easy to understand. If all the members of this product have a positive column, then we in fact get the convergence property that we want. Now I want to explain why that's true. Okay, each matrix has a positive column. Why is this true? In order to answer this, one way to answer this is to introduce what I'm going to call a consensus semi-norm, fancy terminology. I'm going to first be motivated by something called induced norms, which hopefully you've seen before. And just to remind you, an induced p-norm on the linear space of n by n matrices, written double-line subscript p, and p is an integer, is a norm, like any other norm, for which the submultiplicative property holds. And the ones which are commonly used, the three of them, the one norm, which is concretely obtained by taking the absolute values of the entries in the matrix and adding up the columns and then looking at the largest number that you get. You have n numbers, one for each column. The infinity norm, the one on the right, is the opposite. You take the absolute values of the entries, you add them up, and they give you each number, then you look for the largest number. So guess what? If we're talking about a stochastic matrix, we already know that the entries are positive, so we don't need, not negative, so we don't need absolute values. And if we add them up, we get the same number for each row. So the infinity norm of a stochastic matrix is 1. That means that matrix is what's called non-expansive. If you take products of it with itself, the products won't blow up. So we have that immediately, and it kind of is a big hint that there's something nice about the infinity norm in dealing with stochastic matrices. Just the induced norm that you may have seen more than any other from a calculus course or a linear algebra course is the induced 2 norm, which is the largest singular value of M, which is more precisely largest eigenvalue of M transpose M. All of these norms satisfy the submultiplicative property. So let's try to get another norm which is relevant to stochastic matrix for our purposes. For each P and any matrix M, let's use the symbol vertical lines with a subscript P to mean the minimum with respect to row vector D of the P norm of M minus 1 D transpose. Does this make sense? We're minimizing, but the space over which we're minimizing is neither closed nor bounded. But we do know that a continuous scalar-valued function on a closed bounded set or a compact set attains its maximum and its minimum. But this is not a compact set. So what are we going to do? For any number sufficiently large, if I define the set of Ds for which this is true, it's going to be non-empty. And for any such R, it's pretty easy to see that this definition implies this. So that this object, which is going to be called a seminorm in a moment, is well defined. Notice that it is always greater than or equal to 0, no matter what M is. Just look at the definition. Secondly, I think it's not hard to see it's homogeneous. If you multiply M by a number R, you can factor R out with absolute value signs. And thirdly, the triangle inequality holds. These three properties mean that this object is what is known as a seminorm. It's the name for it as an algebraic object. If it were true that this equaling 0 were to imply that M equals 0, then this would actually be a norm. But it's not true. M equaling 0 does not imply that this is equal to 0. So we have a seminorm. Additional properties of M. It's less than or equal to 1 if the norm is less than or equal to 1. That says the infinity seminorm of a stochastic matrix is less than or equal to 1. Secondly, this is not a property but a definition. We say M is contractive in the P seminorm if this inequality holds. And thirdly, I'll just state that you can prove that if M is a subset of matrices in Rn whose row sums are all equal, that is, let's let M be such a set. That is, if for any such set of matrices M, it is true that M times 1 equals span of 1, then the submultiplicative property holds. This is a 4-line proof. Fortunately, stochastic matrices falls in this class of M's, so when we're dealing with stochastic matrices, we have the submultiplicative property. Why is the consensus norm important? You're going to sit down, I hope. Okay, so I'll now make a statement. Suppose M is a subset of matrices whose row sums are all equal, and let P be any positive integer, and let C be a closed bounded or compact set of contractive matrices in the P seminorm. And let lambda be defined this way. So lambda is going to be well defined because C is a compact set, and lambda is going to be a number less than 1 because all the matrices in this set are contractive. What this says is that any infinite product of matrices from the set C will converge as fast as lambda to the I converges to 0 to a rank 1 matrix of the form 1C star. Star doesn't mean anything here, it's just a symbol. So this is the value of the semi-norm. Now wait a second. I just talked about this word converge. What is that all about? What's convergence? Huh. Okay. Supposing you want to walk from A to B. Okay? One way to do it is to walk like that, right? Another way to walk the same is like this. Same distance both ways, right? Either way, same distance. Or if you have smaller feet, you could take smaller steps, same distance, right? Or even smaller steps, same distance, right? Or straight line, same distance, right? So Pythagoras was wrong. This is what I call a fuzzy proof. And I believe it or not, I once went through this exercise. I don't know if many of you have heard of Latvizada, the inventor of fuzzy logic, fuzzy sets. And we had a good laugh a long time ago using this. Okay, back to this result that if we have a bunch of matrices which are contractions in the semi-norm, then we get convergence to a rank 1 matrix, and we even have a convergence rate. And this is a consequence of the submultiplicative property, because what the submultiplicative property implies more or less immediately, if you use it here, that this product will be less than or equal to lambda to the ith power. And that implies immediately that the limit goes to 0. But what it does not imply is that the limit of the matrices go to 0, which is really what we want. It only implies the limit of the semi-norm goes to 0. But it is true nonetheless, but it takes a little proving to show that, in fact, this limit is correct, although it's not a one-liner, it's 10 lines. So what we can conclude is this. If S is a complex set of stochastic matrices, members have at least one, this is what we want to prove. This is what we just went through, and we want to use this to prove what I mentioned before, that if we have a bunch of stochastic matrices which all have positive column, then the product converges and we reach consensus. And from what this says, all we have to do is to show that each of the matrices in this product is contractive in the infinity semi-norm. That's all we have to do, if S has a positive column. So why is this true? This is actually pretty easy. So I can take any stochastic matrix S and decompose it into the sum of two matrices. One matrix is of the form 1C, and the other one is what's left over. C is the largest row vector for which S minus 1C is non-negative. So you keep fooling around with the entries of the row vector C and watch what happens to S minus 1C, and you want to let the entries of this row vector get larger and larger, just so long as you don't make the overall matrix S minus 1C have any negative entries. I'll give you a numerical example in a second. It's very easy to do. And then you define T. So notice that T times 1 is equal to S times 1 minus this, and if little algebra says that T1 is equal to 1 minus C1, that's scalar, times the 1 vector. So that's an eigenvalue of this matrix. So all row sums of T are equal to this number. And so if I were to compute the infinity norm, not semi-norm, but the infinity norm of T, it would be this number. keep in mind that T is non-negative. Moreover, think about it, C is not equal to 0 if and only if S has a positive column. If C has a positive, is not equal to 0, then this must be less than 1 if and only if S has a positive column. So that says the infinity semi-norm of such an S, which is defined to be equal to this, is less than or equal to this because this is the minimizing value that sticks in here. So I have a less than or equal if I stick in a C, which I've already come up with. But the thing inside the lines, vertical lines, is T, and I've already said that the infinity norm of T is 1 minus CS, and this is less than 1. Here's a numerical example of this. I start out with a stochastic matrix. The first column is positive, the third column is positive, and I try to find as large a number as I can in the first position over here. So when I take this vector times this and subtract it from the first column, nothing goes negative. Obviously, the limiting term is going to be this 0.2, and that's where this 0.2 comes from, and that produces a 0 over here. Same reasoning with the third column. The limiting term is going to be this. That's where this 0.1 comes from, and that produces 0 over here. And if you look at this matrix, this is T, and its row sums are all 0.7, and so it is a contraction in the infinity norm. And so S has the required property. So this is very simple. We've basically just proved this. Now what I want to do is to make a transition from matrices, which is what we've been talking about, to talking about graphs. Notice that as we talked about the matrices, we were really dealing with just the zero, non-zero pattern in the matrix, and the matrix was non-negative, a stochastic matrix. That suggests that the critical properties of the matrix that are needed can really be described by a graph. And in my mind, a graph is you have a 1,000 by 1,000 matrix. All you have is, 10,000, 100,000 numbers. But if you have a graph, well, it's still pretty complicated, but at least you can see something like a picture. And to me, it's a little more informative. So let's make the transition. To do that, we need to define the graph of a non-negative matrix. So that there are various ways to do it. It's that matrix, it's that graph whose adjacent matrix is the transpose of the matrix, which results when all the non-zero entries of M are replaced by ones. A lot of words. In other words, for a non-negative matrix M, gamma of M is that directed graph which has an arc from I to J whenever MJI is non-zero. So there's an example of a matrix. Suppose that all the M's are positive and all the zeros are 0. So if you were to write down the graph of this matrix, it would have the 3 diagonal entries are positive, so we'd have 3 self-arcs corresponding to that. And there will be an arc from 1 to 3 because M31 is positive. And the same with the remaining. So it's very simple to write down such a graph. Now, if you could ask, well, okay, what is the graph of a flocking matrix determined by a graph N? Guess what? The graph of the flocking matrix is going to be the same. You look at the definition, D inverse is just a diagonal matrix. It's just scaling the entries in this matrix, but it's not creating or any non-zero entries or eliminating them. So the graph of this product is the same as the graph of this matrix by itself, which is what is said here. And the graph of this matrix is the transpose. This is the adjacency matrix of n, and so the graph is equal to n. And so what this says is, as I advertised before, there's a bijective relationship between a flocking matrix and neighbor graph n. Now the graph let's define a strongly rooted graph to be a graph which has at least one vertex which is adjacent to every other. That means that I have to be able to find a vertex, in this case this one, for which there is an arc to every other vertex in the graph, right? There's an arc there, there's an arc here, and there's an arc here, and there's an arc here. So this is a root, and it's strongly rooted because we can get to any other vertex in one hop. Motivation for strongly rooted. For any non-negative matrix n, the graph of M has an arc from I to j whenever mji is non-zero. And if you think about it for a second, that means the graph of M is strongly rooted if and only if M has a positive column. So we had this result stated in terms of matrices. If we have a bunch of stochastic matrices which all have positive column, we get convergence. I can restate this. If we have a bunch of stochastic matrices whose members each have a strongly rooted graph, same result. We get convergence. Now the problem with this is, of course, that we're talking about a pretty restricted set of stochastic matrices. So we want to broaden the class of stochastic matrices for which we can make statements about convergence. So this is the problem we want. We don't want to just deal with matrices with positive columns. So one thing you could do as a first step is you could try to break up this product into subproducts of length m. M is just some integer you pick. That's the first m, the next so many m, and the next so many, and so forth. So if you could do this in such a way so that each of these products had a positive column or had a strongly rooted graph, then I could apply what I just said to these products and make a statement about convergence. And once I had this last term wouldn't cause any problems because r times 1 was equal to 1. It's a product of stochastic matrices. So the question really is, to establish convergence of an infinite product, this boils down to determining when the graph of a finite product of stochastic matrices is strongly rooted. Okay? So let's try to dig into that. As before, let script G be the set of all directed graphs on vertex sect 1 through n. I need an operation on graphs, and I call that composition. So we'll say that a graph G2 is composed with G1, and we write as G2 circle G1. Is that directed graph in G, which has an arc from I to j, whenever there's an integer k such that ik is an arc in G1 and kj is an arc in G2. Yeah, that's a little cryptic, but we can make it a little clearer. What motivates the definition? If I look at the product of two square non-negative matrices, I look at the jth entry of the product. As you all know, it satisfies this formula. So this number will be positive if and only if there exists an integer k so that both a jk and a ki are positive. Therefore, ij is an arc in the graph of C if and only if for some integer k, ik is an arc in the graph of A and jk is in the graph of B, which is basically what we've already defined. If you put this all together, what this really means is we've defined composition of graphs in such a way so that the graph of the product of B times A is the composition of the graph of B times the graph of A. One thing I'll mention at this point, which is quite important, is that if B and A both have positive diagonal entries, then when you do the composition, you don't lose any arcs. In other words, the set of arcs of the product contains, possibly as a subset, the set of arcs of B union the set of arcs of A, but it may contain some more. You never lose any because of the positive diagonals. Okay, this is just a restatement of what I said before. So deciding when a finite product of strongly matrices, of stochastic matrices, has a strongly rooted graph is the same as deciding when a finite product of graphs is strongly rooted. So when is the composition of a finite number of graphs strongly rooted? You need another concept. You need the concept of a rooted graph, which is more or less existing concept from the graph theory literature, although this exact term is maybe not commonly used. This simply means there's some vertex in the graph which has the property that you can drive from that vertex to any other vertex in the right direction and reach any other vertex. This is an example of a rooted graph. All three of these vertices are roots. If I start here, I can get to this vertex going in the right direction. I can get to this vertex and going in the direct direction by going here first and here second. And then I can get to this vertex going one more step, and I can get to this one in one hop. And same for the other two. So a rooted graph can have multiple roots, but the notion of rooted is what we need. Okay, now I state without proof. This is almost a problem in reachability theory, like reachability from controllability, which says that every composition of n-1 squared or more self-arc rooted graphs is strongly rooted. So if you compose enough self-arc rooted graphs, you get a graph which is strongly rooted. So that enables us, and in addition, the set of self-arc rooted graphs is the largest set of graphs for which has this property. So we already have this result. If we have strongly rooted graphs of the stochastic matrices, we get convergence. And now we look at another product of a bunch of stochastic matrices and assume that they're all rooted. Then we know if we break this product up into smaller products of length m, where m is n squared, n minus 1 squared, I think that's what it was, n minus 1 squared and so forth, then each of these will become strongly rooted. We can apply this result and get our convergence result. So the end of this is that if we merely have self-arc rooted graphs and we take an infinite product, we will get convergence, and the convergence will be exponential. We can generalize this even further. Let me introduce another term. Supposing I have a bunch of graphs, I'll say that the sequence, it's a finite sequence, is jointly rooted if when I take the composition, I get rooted. So some of these graphs may be not even connected, which would be very good if you're trying to study robustness or what happens if you have communication breaks or things like that. So let's define an infinite sequence of graphs to be repeatedly jointly rooted. If the first so many is jointly rooted, the next so many is jointly rooted, the next so many is jointly rooted. And then we can break up a product of stochastic matrices in connection with this, similar kind of reasoning, and reach the conclusion that if S is a compact set of stochastic matrices of members self-arced, and each matrix. Well, this is what we had before. This was rooted. Yeah. I just wrote down, I was reminding you what we had before. From this and this reasoning, we can reach this more general statement that if we have repeatedly jointly rooted sequences, then we get convergence, provided, there's a catch here, that the set from which the matrices are coming is closed. And that is a little bit of a catch. We need that in order, if you look back at the other results, I'm talking fast, so you might have forgotten, but you do need this compactness property. Compactness is not in general, compactness of S does not in general imply compactness of the subset. Fortunately, it does for if S is finite to begin with, that means that this set is also finite. It also is true if the stochastic matrices are all bounded below by the entries are bounded below by positive numbers. And this is important if you want to study the convex combination rule. In any event, putting this all together, we end up with the main result on flocking, on consensus, which is this. If we have the flocking problem and we're looking at a sequence of neighbor graphs which is repeatedly jointly rooted, then indeed we reach consensus, and we reach it exponentially fast. Now, this result generalizes automatically to the interesting situation when one of the agents in the group is a nonconformist and ignores the update rule and just does what it wants to do. It moves in some arbitrary but fixed direction, theta 0, and all the other agents don't even know about this. They're clueless. They just keep following the Visek rule. Suppose the remaining agents are unaware of this and follow the Visek rule. Under these conditions, agent K has no neighbors to follow, which means that the vertex of vertex K of any neighbor graph cannot have any incident arcs. Because of this, the only possible way the graph could be rooted or strongly rooted would be a vertex K would be a root, and the only root. And from this, one can conclude that all the preceding results continue to be applicable without any changes. In other words, if the agents of the group will eventually all move in the same direction, they'll move in the direction that the nonconformist is already moving. So here's some simulations of this behavior. The red agent, if you can make out, that's the red one, is moving and the other agents are following it. Now this is cheating a little bit because he's going around in a circle and the theory only allows him to go in a straight line. But if he moves slowly enough, the other agents respond quickly. Here's a more detailed simulation. And I guess the red agent, the leader, is moving just moving in one direction. Yellow are the neighbors of the agent, and you notice they change with time. I'll run that again. So the yellow are the neighbors of the leader. And of course, the other agents it is a directed graph, so the other agents also have neighbors and so forth. And everybody ends up moving in the same direction. And if you want to, you can play even more games with this, and agents better be moving slowly for this to apply. You're going to have fun with this kind of stuff. Okay, so that brings me more or less to the end of the discussion on consensus. But I did have more material which I wanted to talk about, but I just don't have the time. But I will make two statements. One of them is, you can ask the question, how does the consensus problem formulated and solved when the agent's clocks are not synchronized with respect to each other? So each agent has its own clock and still following the Visick rule, what happens? And if you think it through, even formulating the problem requires more thinking, because you have to make sure that your neighbor's headings are well defined at your clock times. So you have to change the formulation of the problem a little bit. This has been worked out, and it's called asynchronous consensus. The other thing I wanted to point out is some very recent discovery. So in 2011, the semi-norm that I've been talking about for a stochastic matrix was said to be equal to this formula. This particular thing on the right comes out of stochastic matrix theory, and it's called the coefficient of ergodicity. And obviously, it's something you can compute. You can compute the number. But what's not true is the statement is false. This was in a paper which was published in the Proceedings of the IEEE. The title of the paper is called Deterministic Gossiping. I'm one of the co-authors, and we discovered that recently, 14 years later, that it's wrong. I don't have enough time to explain how that all worked out, but I was teaching this material in my course, and I was trying to prove something. I couldn't prove it, and eventually realized it was wrong. How to deal with this issue, and it has been dealt with. It's not been corrected. It is a false statement. How to deal with this issue, there's another way to do it, by introducing another kind of a consensus semi-norm. This will be discussed at the forthcoming CDC in Brazil in December, for those of you who are planning to go. There's a paper on this. So at this point, I'm told I have an hour and a half, and that gives me about 25 minutes, which I probably won't be able to cover everything I'm about to talk about, but I'll do my best. This is a different problem. It's called distributed averaging. And I want to explain what it is, and then dig into a little bit, tell you what it's used for, and so forth. So let me just review consensus, so for sake of comparison. And then we'll talk about, hopefully, linear iterations, gossiping, periodic gossiping, multi-gossip sequences, request-based gossiping, and finally something called double linear iteration. So it's a lot to do in 25 minutes. I don't think I'll make it, but I'll start. First, consensus and averaging. So just to review what we've just talked about, restated in a slightly different way. So we have a group of n agents, and we have a neighbor graph. Except in this case, I'm going to take the neighbor graph as being undirected, and I'm going to assume it's connected with vertices. Here, each agent's neighbors does not include itself. So the neighbors of agent 2 are 1, 3, and 6. It's the adjacent agents. So each agent's neighbor is still well defined, but it does not include itself. The neighbor of agent, okay, I just said what that was. Each agent I controls a real scalar variable, time-dependent variable, which we're going to call an agreement variable. And the goal of consensus, which we've already looked at, is for all n agents to ultimately reach a consensus by adjusting their agreement variables to a common value. It's pretty much what we've talked about, except we're using an undirected graph. This is to be accomplished over time by sharing information among neighbors in a distributed manner. The consensus process is a recursive process which evolves with respect to a discrete time scale. In the standard consensus problem, we use averaging, which I've already talked about. And this is the Visick formula. It looks a little different. The reason the 1 is here, because I'm no longer including myself as a neighbor of myself, so I have to account for that. So this 1 plus this is what we had seen in the preceding formula. And the reason I'm breaking it apart now is I want to compare this with distributed averaging. And the reason xi is not in this sum is because I is not in this set. But it's basically the same. Still the average. Okay, what about an averaging process? How does this differ? First of all, an averaging process is a consensus process, except that the average, the value to which the agreement variables are to converge, instead of being an arbitrary number, it's the average of the initial values of the agreement variables. That's the difference. In other words, this is what all of the agents are supposed to end up converging to. They don't know what this is because they don't know the values of the x except for those of their neighbor. What are the applications? Well, temperature calculation, but the big application is distributed optimization. There are a bunch of algorithms out there for doing distributed optimization, either unconstrained, or I think there are even some constrained distributed optimization results, and they're all using explicitly or implicitly distributed averaging. And there is an open research question here because distributed averaging requires some network-wide information that you might not want to assume is required. So the question is, can you end up doing distributed optimization without doing distributed averaging? And that I don't know the answer to at this point, or some version of distributed averaging. Some generalizations of this problem. Time-varying case when n depends on time, and that's been looked at. In the integer-valued case, some of you may have been at the seminar, this lecture a few years ago when Tamar Bassar gave the talk. He looked at the integer value of this case with another guy from the University of Illinois, and that problem is particularly hard, like many integer value problems. The asynchronous case, what happens if each agent has its own clock? There are implementation issues. How much network information does each agent need? To what extent is the protocol robust? There are various performance metrics looking at different algorithms. Convergence rate's the obvious one, but you could also talk about the number of transmissions needed. Transmissions cost money, they cost energy. They can, if somebody is going to try to break your network, the more you transmit, the higher the probability that they'll be able to break it. The two general approaches to distributed averaging. One is probabilistic. I'll explain where that arises in a moment or two. And the other is deterministic, which is the way we're going to look at the problem. We'll make as a standing assumption that the neighbor graph is always connected. The first thing I want to talk about are linear iterations. So what do we mean by linear iteration? I mean a linear recursion equation which looks something like this, where n is, as usual, the set of indices of h and i's neighbors, and the wij are suitably defined weights, non-negative weights typically. So supposing we rewrite this as a state equation. Define W equals Wij, where Wij is the ijth element, and when we don't have a Wij, then we stick a 0 in the matrix in that position. And if we do that, then we get a recursion equation like this. What we want is for the state vector x to go to the average. This is the average of the initial values of all the components of the x vector times the one vector. That's what we want. It's a little different than before. So I'm now state a theorem which those of you who have taken a linear algebra course or a control course should be able to understand most of this right off the bat. If A is a real n by n matrix, A to the t converges to a rank 1 matrix of the form QP transpose if and only if A has exactly one eigenvalue at 1 and all the remaining n minus 1 eigenvalues are strictly smaller than 1. In other words, if all the eigenvalues except for 1 are inside of the unit circle and there's one eigenvalue at 1 on the unit circle, what that means when you take the powers of A, that all those eigenvalues inside the unit circle and the eigenvectors and everything that goes with them, that all goes to 0 because the eigenvalues are inside the unit circle. And you're just left with the eigenvalue on the unit circle and its eigenvectors. So Q and P transpose are eigenvectors, not surprising. So this should not be surprising to you. And the fact that P transpose Q is equal to 1 takes a little bit of work, but it's no big deal. So this is a theorem which very much relates to what we want of W. Suppose W is such a matrix and that 1 is an eigenvector for eigenvalue 1 for both W and W transpose. Then if I said Q equals the 1 vector, then P would have to be, because of this, 1 over n times 1, and therefore W would have to converge to this matrix. And therefore X would converge to this matrix times the initial state, which would be equal 1 times the X average. So this is what we want. Now, if we add the additional assumption that the weights are non-negative, then we have we have a more special matrix. Let me remind you that a stochastic matrix is a matrix with only non-negative entries and row sums all equal 1. That's what we've been playing with so far. And this is true. A doubly stochastic matrix is a matrix which is stochastic and its transpose is also stochastic, which means that it's a matrix of non-negative numbers and its row sums are equal to 1 and its column sums are equal to 1. And it looks like, if you look up here, that this is the kind of matrix that we want, a doubly stochastic matrix. I mentioned that, as I mentioned before, that the infinity norm of a stochastic matrix is 1, so it's non-expansive in the infinity norm. The spectrum of that says the spectrum of S is O no matter what, as long as it's a stochastic matrix, its eigenvalues are contained in the closed unit circle in the complex plane. That's the only way it can be non-expansive. That's true for every stochastic matrix. And moreover, the eigenvalue 1 must have geometric and same geometric and algebraic multiplicity. Those of you who know about the Jordan normal form, you can't have any Jordan blocks which are bigger than 1 by 1, because if you do, 1 by 1 blocks just give time functions of the form lambda to the tth power, but for example, a 2 by 2 Jordan block gives t lambda to the tth power, and that t is going to kill you if lambda is equal to 1. You'll have instability. So we can't have that, and we know we can't have that because of the non-expansive property of a stochastic matrix, and that leads one to conclude that geometric and algebraic multiplicity are both 1. Algebraic multiplicity is the number of times the root 1 occurs in the characteristic polynomial of the matrix. The geometric multiplicity is the dimension of the null space or kernel of 1i minus a. If I said that right, sometimes I confuse those. Thus, for a non-negative matrix, X at T converges as we want it to, if and only if W is doubly stochastic and a single eigenvalue at 1 and all the other eigenvalues of magnitude less than 1. How does one choose the Wij's to have these properties? So here's an easy way to do this. Very easy. So this is the This would be W. What is L? L is called a Laplacian matrix, but we don't need that in this talk. Just it's the difference between a diagonal matrix of in degrees and an adjacency matrix of a graph. Is adjacency matrix of n, which I've already defined. So why does this work? Let's look at this carefully. First of all, G is larger than all of the numbers on the diagonal. That's the requirement of G. So why does this work? Notice first that I minus 1 over G times D is a diagonal matrix whose entries are all positive because we've scaled down the entries of D with 1 over G. So if I subtract this from the identity, I will still end up with a diagonal matrix whose entries are all positive. Now, I minus 1 over G times L is I minus 1 over G times D plus 1 over G times A, but A is already a matrix of non-negative numbers. If I add such a matrix to a matrix of non-negative numbers, nothing goes negative, so the whole matrix has non-negative entries because of this. The other property that I need is gotten by the fact that the one vector times this Laplacian matrix is equal to 0. That's a standard result in graph theory, and it's also a very easy consequence of the structure of this matrix. And that enables me to say, if this times 1 is 0, then obviously 1 times the identity is 1. So I have this, and because of symmetry, I have it the transpose. So this is a doubly stochastic matrix. So this is the kind of matrix which does the job. I haven't explained that the geometric multiplicity, that there's exactly one eigenvalue at 1. I haven't done that, so I'm cheating. Why is a single eigenvalue at 1? Because all eigenvalues are not, I forgot, I'll have to skip over this. I forgot the reasoning. But anyway, this is what this looks like on a per agent basis. This would be the update rule for a particular agent. And you notice that the agent would need to know G. That means that the agent must know an upper bound on all of the neighbors of all the agents in the network. And that is a network-wide assumption which you may or may not want to make. Now, there's a better solution. This solution was in a paper that Steve Boyd wrote some years ago, and I'll just sketch it for you. It turns out, amazingly, I think, that this Laplacian matrix is also a positive semi-definite matrix and can be factored like this. And Q is actually an incidence matrix for the graph that determined L. This is all part of Laplacian theory. Oh boy, I thought I'd worked this out. Let me tell you what's going on here. That funny symbol. So this particular slide I made years ago, and I used some software which enabled me to insert LaTeX symbols into the slide. So this was software developed by a guy at Berkeley. It was actually very nice. And he stopped supporting it, and I had to change the software. I had to change to a different software, and the software I'm using now is even nicer. But this is a new computer with a new version of PowerPoint, and apparently the old software doesn't work in the new version of PowerPoint. That sounds like a fire alarm. So this is supposed to be a diagonal matrix. That's supposed to be the symbol that's in here, but I've been chasing this for the last week, trying to make these corrections, but I don't know why I didn't see this earlier today. I think it made up its own mind. In any event, this lambda should be in here. Lambda I is equal to this. And so the update equation in matrix form looks like this. And this indeed is a matrix with the required properties. And there's that symbol, like, oh, I know what's going on. It's supposed to be this matrix. And the per agent version looks like this, rather than looking at the matrix version. And 2 comments. This is called the Metropolis algorithm, not because Metropolis was a city, but because Metropolis was a mathematician in the 1950s. I guess he was pretty well known. And he came up with an, I'm not exactly sure what his part was in the contribution that led to this, but I guess he gets a lot of credit. This was, I believe, in Steve Boyd's paper, this algorithm. And notice that to implement this, agent I needs to know dj, which is the number of neighbors of its jth neighbor. So the assumption is that each agent needs to know the number of neighbors of each of its neighbors, which is still a pretty strong assumption. So if you're trying to advance the state of the art in distributed optimization, keep this in mind, because this is the kind of assumption, maybe not this particular one, but something like this, which people have to make in order to do distributed averaging, which is what distributed optimization seems to depend upon at this point. So you can also count up the number of transmissions. I'm going to skip over that. It's not important. Let me talk a little bit about gossiping in the last few minutes, and then we'll probably have to call it quits. I want to explain to you what gossiping is without going into any details, because there's another emergent behavior. Gossiping is a clever idea. And there's been a lot of study of gossiping in the signal processing literature. So this is what's called a gossiping process. So gossiping process is a consensus process which at each clock time, each agent is allowed to average its agreement variable with the agreement variable of at most one neighbor, one of its neighbors. So if agent I and J are neighbors and they decide to gossip, agent I updates its state to be the average of the state of itself and its neighbor J. Now, neighbor J must be, right, so that's what this is. If agent I gossips with neighbor J at time t, then agent G must gossip with agent I at time t. So there has to be, and this is one of the complexities, there has to be agreement between 2 agents in order to gossip. Okay, now why is that being forced? This is called a gossip. In the most commonly studied version of the problem, the gossips are determined probabilistically. So you've got a neighbor graph. A pair of agents gossip at the present time, maybe another pair as well. That's called a multi-gossip. Who gossips with who has to be determined. If you try to do it deterministically, for various reasons, you can run into deadlock. The whole network can freeze. So the easy way out of this is to do it probabilistically, and that's basically what a lot of people have done. Although there are deterministic solutions, they're more complicated. Putting that aside for a second, let's suppose, let's just try to understand what gossiping has to do with consensus. So a pair of agents are doing this, supposing that other pairs might also be doing this, or if you're not gossiping, you do nothing. You don't change your variable. So either your variable value remains unchanged, or you gossip with another agent. Look what happens when you got 2 agents gossip. You add things up. Notice that the sum of the 2 variables at time t plus 1 is the same as the sum at time t. Now, if everybody in the network is either gossiping or doing nothing, What does that mean? That means the sum total of all agreement variables across the network doesn't change, the sum total. It's redistributing, the values are redistributing, but they're not changing. What does that mean? It means that if you reach a consensus, in other words, everybody's value is the same, it must be the average of the initial values. You see that? That's an emergent behavior. I have nothing up my sleeves, I just said that. You should be able to see. That's an emergent behavior. And that's what gossiping is all about. And the complexity in the deterministic case arises because generally one agent says to another, would you like to gossip? Now, the other agent's sitting there, and if he gossips with you, he can't gossip with anybody else. But supposing at exactly the same time he's being asked to gossip, he's being asked to gossip by you, you're being asked to gossip by somebody else. So you have a conflict. How do you resolve that conflict? And one way to do it is to flip a coin, which gets you into the world of probabilistic behavior. Okay, so I do have a lot more slides, but it's almost dinner time, and you've been very nice. And so I'm going to say thank you very much. There are open research problems to be thought about. I've already discussed one with you. There are others. Thank you.